Hi, I'm Gabriel Chen, and welcome to Lab 5, the Human Rocket. The purpose of this lab was to examine a unique case of a falling object. What makes this particular case interesting is that the opposing drag force is dependent on multiple changing variables, including fluid density and velocity, as well as that the starting height is of significant magnitude to alter the force of gravity by a measurable amount. This is modeled both experimentally and computationally using a skydiver jumping from the upper stratosphere as the example case. The jumps were formed by Felix Baumgartner in an effort to achieve the first supersonic skydive. A computer simulation of this was created using the program GrowScript. This unique situation allows us to examine the falling object in a situation where the terminal velocity is non-constant. These are the relevant equations to model the situation. They allow us to determine how the forces will be altered as the skydiver progresses. Here is some further elaboration on the drag force as well as a video of the actual skydive and the speed of sound that he is striving to break. This is a comparison to the real-world data accumulated by the scientists monitoring Felix Baumgartner's dive and the data produced by my GrowScript simulation of the fall. Both datasets show the skydiver achieving supersonic speeds and a peak in speed at approximately 50 seconds, followed by a decrease in velocity. The computer simulation achieved far greater speeds. I believe this to be because of the assumptions made by the computer model. This included a constant drag coefficient and a cross-sectional area that is also constant. In reality, the cross-sectional area should be in constant fluctuation as the skydiver adjusts its posture and positioning, and the drag coefficient should be increasing from near zero as there is a negligible air density in the upper stratosphere where the jump began, which would cause a non-existent or negligible drag force at the very beginning. These are some of the observations from both the real-world and simulated models of the skydive. Of particular note from this analysis was the model of drag force used. Dropping from the upper atmosphere resulted in a drag force that required far more considerations than a drop from a lower altitude. The changing air density throughout the atmosphere needed to be accounted for, not just a drag coefficient and a changing velocity. Indeed, it is this drop from a location with essentially no drag force that allows the skydiver to achieve supersonic speeds. As is, the skydiver's velocity is allowed to accelerate freely from gravity with little opposition by drag until he reaches denser layers of the atmosphere. This all-important air density is modeled by these equations, which depends on both altitude and temperature. This accompanying model of the air density of the atmosphere is what allows us to more accurately model the nuances of the drag force. It also shows how the change in temperature with altitude affects our model's predictions. Temperature is a major factor in the atmospheric pressure and thus the air density, which in turn influences the magnitude of the drag force throughout each atmospheric zone. Here are some other considerations and elaborations taken into account by the computational model, some specifics on what assumptions are made, as well as some of the data taken from the video of the skydive. A particular note are the drag coefficient and the cross-sectional area. The drag coefficient is assumed to be a constant 0.7 for simplicity, as that is the average drag coefficient for a human in less extreme atmospheric conditions. The cross-sectional area assumes that Felix Baumgartner is always in a position with his head tilted downwards. This assumption is made because there is no simple mathematical model to keep track of his changes in posture throughout the entire dive. This is the code for our GrowScript model. Line 29 to 67 initialize many of our initial conditions. For example, line 29 sets the skydiver's mass to be 110 kilograms, and line 32 and 33 set the skydiver's initial position and velocity. A particular note are lines 58, 61, and 64. These are the mass of the Earth, the gravitational constant, and the radius of the Earth. These allow us to determine the gravitational force throughout the skydive as the distance between the center of the mass of the Earth and the skydiver varies significantly. Meanwhile, lines 81 to 89 calculate the air pressure. Various formulas are used depending on the altitude of the skydiver at that moment. Air pressure is then used in line 90 to calculate the air density. The air density is then used to calculate the drag force, which is then combined with the weight force in lines 94 through 96. The net force is then used to update the velocity and position of the skydiver in lines 100 and 102. This page describes the data we had in the previous page. In conclusion, we were able to examine the nuances of having multiple variables affect an opposing force in the situation of a falling object.